Here we're going to look at how we can relate deviations from Raoult's law, from ideal behavior, how they correlate with whether the heat of mixing is positive or negative. And so let's start off by first looking at the ideal case. So for the ideal case, the pressure above a liquid mixture is the mole fraction of component A times the saturation pressure of A plus mole fraction of B, saturation pressure B. This is just from Raoult's law, and that corresponds to this line. An ideal behavior implies that delta H of mixing is zero. This also has the excess enthalpy. So we want to compare this to where we have deviations from Raoult's law. So let's first look at positive deviations. So by positive deviations, we mean the bubble pressure, this curve, is above the ideal, the Raoult's law curve. And so that means the pressure XA, gamma A, PA sat, and of course XB, gamma B, PB set. So positive deviations mean gamma A, gamma B are greater than 1. And corresponding to this, we show here an enthalpy mole fraction diagram. And I'm not trying to imply that these were all generated for the exact same system. I'm just trying to show you the general trends that when we have positive deviation of Raoult's law, then we have the delta H for mixing is also positive, which means mixing is endothermic if we mix the two pure liquids. So this is ideal solution and then the blue curve, so we can ignore this curve. The blue curve corresponds to the enthalpy of the mixture. So positive deviations mean the molecules go into the gas phase more readily than an ideal solution. And this is because the intermolecular forces between the unlike molecules, the A and B molecules, is less than the mean of the pure liquids. So let's look at, just make up some numbers to help visualize what we're talking about. So I'm not going to put units here. I'm just saying let's suppose the interaction between A and A molecules, the forces that keep A in the liquid phase, let's say that number is 20 in some energy units, and for the B molecules, it's 30. In the mixture, then, we're going to have interactions between A and B molecules also. And for the case we're showing here, this number is going to be smaller than the average. The average is 25. I picked 18, so in this extreme, meaning it's much easier for breaking those bonds holding the not chemical bonds, but the bonds holding A and B molecules in the liquid phase, and therefore we have a pressure higher than what's predicted by Raoult's law. Well, let's look at the other extreme of negative deviations. So I've again written down the equation for a non-ideal. However, for negative deviations, gamma A, gamma B are less than 1, and so the bubble pressure line here, which is what this equation is lower than the Raoult's law, lower pressure Raoult's law equation. And correspondingly, the delta H for mixing is less than 0, so it's exothermic. What this means then is that the forces between molecules in the mixture are actually stronger than the forces between the molecules in the pure liquid, between the average or the mean of those forces. So again, if we make up numbers that don't correspond to any particular system, and not assigning units, but just the concept that these are the relative energies, bonds holding these molecules in the liquid phase, if you like, and we look at the AB molecules, and let's say this number is 29, so the average would be 25. Say we had a 50-50 mixture, you can see that we have much stronger bonds, so molecules are less likely to go in the liquid phase. This is negative deviations, so negative deviations, delta H of mixing is less than 0. So you notice the trend in both cases, both the Raoult's law and ideal mixing enthalpies, both cases the system we're looking at is below the ideal case.